Governments and automakers worldwide are implementing a transition toward E20 and E25 ethanol-blended fuels for internal combustion engines. As this rollout moves forward, consumers and automotive journalists are reporting a consistent friction point, a noticeable loss in fuel efficiency. Many attribute this mileage drop to bad gas or variations in fuel refinement, but the reduction in range is not an arbitrary penalty. It is a strict consequence of thermodynamics. To understand this loss, we have to trace the behavior of ethanol from its molecular properties through computational simulations to real-world road test data. The success of these mandates depends on how ethanol's unique chemistry changes the combustion envelope of a legacy engine. We start at the molecular level. Compare the complex hydrocarbon chain of gasoline, C8H18, with ethanol, C2H5OH. Ethanol carries its own intrinsic oxygen atom. This structure determines the lower heating value, or volumetric energy density. Gasoline contains 30 to 33 megajoules per kilogram, while ethanol peaks at 26.8. By volume, ethanol provides approximately 34% less energy. Ethanol also absorbs more heat when it vaporizes in the cylinder, 923 kilojoules per kilogram compared to just 346 for gasoline. This changes the stoichiometric air-fuel ratio. Gasoline requires 14.7 parts air to 1 part fuel for optimal combustion. Ethanol requires only 9. Ethanol requires less ambient air because it brings its own oxygen molecule into the combustion chamber. These theoretical properties are verified in automotive engineering tables, showing the consistent gap between the two fuel types. Ethanol does provide a research octane number of 108.6, meaning it is highly resistant to engine knock. While high octane usually permits more efficient engine operation, ethanol's energy density deficit works in the opposite direction. Ethanol's chemistry means a legacy engine must consume a higher volume of fuel to reach equilibrium, altering the engine's thermodynamic cycle. To model these changes, engineers use computational tools like AVL Boost. This allows us to simulate molecular impacts within a virtual engine. The test uses a single-cylinder, 4-stroke engine, analyzed at a constant speed across varying load conditions. This simulation data tracks the direct impact on engine torque as ethanol percentages increase. Looking at the E30 data line, we see it consistently underperforms pure gasoline across every load percentage. The same trend appears in the maximum power output. The E10, E20, and E30 lines diverge downward in parallel, following the energy deficit of the blend. To maintain the baseline power output, the engine's brake-specific fuel consumption must rise to compensate for the lower energy density. The simulation proves the mileage drop is inevitable. The laws of physics cannot be bypassed by simply changing the fuel. While performance drops, the simulation's emission data identifies where ethanol's chemistry becomes an asset. There is a sharp decrease in carbon monoxide emissions as the ethanol blend increases to E30. Ethanol's oxygen content ensures a more complete burn of carbon, even in rich mixture zones. We also see a decrease in unburned hydrocarbons at high percentage loads. However, the Zeldovich mechanism model reveals a different story for nitrogen oxides. Even though ethanol's high latent heat helps cool the cylinder, the extra oxygen and higher combustion pressures actually increase NOx emissions. Ethanol is not universally cleaner. It trades unburned carbon for nitrogen oxide, shifting the burden to the vehicle's exhaust after-treatment system. Moving from simulation to reality, road tests on E20 compliant vehicles show that different engines experience vastly different efficiency drops. In Autocar India's testing, the naturally aspirated Desire saw a 3.8% efficiency drop, while the turbocharged Creta N-Line fell by 12.6%. The engine with the worst drop is a 1.5-liter turbo with a 10.5 to 1 compression ratio. Turbocharged engines utilize the high octane rating of standard E10 to advance ignition timing, increasing their baseline efficiency. When switching to E20, the engine can no longer extract enough performance from the timing advance to cover the missing energy density, resulting in a steeper perceived drop. The Desire, which limited the drop to 3.8%, highlights the role of the engine's software. This involves dynamic fuel mapping calibration performed by the engine control unit. Sophisticated calibration adjusts the air-fuel ratio closer to ethanol's 9.0 ideal, mitigating the energy penalty in real time. The mileage penalty of E20 is not a static absolute. It is dictated by whether the engine's hardware and software can recalibrate to ethanol's requirements. These technical hurdles explain why governments are hesitant to immediately mandate E25. Millions of legacy vehicles engineered before 2023 have hard limits on backward compatibility. At E25 concentrations, there are physical risks to rubber fuel hoses, fuel seals, and plastic injector components. Ethanol is an effective solvent. High concentrations can strip protective engine deposits and accelerate the wear of older elastomer parts. Software updates cannot protect legacy hardware from the chemical reality of high-blend alcohols. The industry has reached a mechanical wall. Retrofitting older engines for E25 is a thermodynamic and material dead end. The path forward is purpose-built flex-fuel vehicle architecture. Flex-fuel vehicles feature upgraded corrosion-resistant metallurgy and ECUs that adjust instantaneously to any ethanol concentration. This shift is happening globally as a matter of energy policy. We are trading volumetric energy density for agricultural energy security and oxygenated combustion. The transition to ethanol blends requires a molecular re-engineering of the internal combustion engine to respect the laws of thermodynamics.